Hello everybody, welcome back. In this video I'm going to be wrapping up our lesson on radicals and rational exponents, looking at a few different examples of how to tie everything together that we've talked about with rewriting our different exponent rules. And what I'm going to start with today is looking at a warm-up, making sure that you, at least if you're watching this video, know how to rewrite from one form to the other, so either from radical to rational exponent, or from rational exponent to radical form. As long as you're able to move back and forth between those forms, knowing your rule for that, as well as the exponent rules, you should be able to tackle all the problems that we're going to talk about after this. So a brief recap would be that if we're looking at a radical expression and we want to change that to rational exponent or fraction exponent form, our rule is always the same. We take our root, it's like a tree root, and it's going to go on the bottom of a exponent fraction. So in this case, z was the root, z is going to go on the bottom. Powers, on the other hand, are powerful. They're going to go on the top of our exponent fraction. This is one way that you could write the problem. Another way would be with parentheses. But the point is that as long as you are aware that roots are like tree roots, they go on the bottom of an expression, and y being the power, it's powerful, goes on the top of the exponent fraction. Okay, that's one way that you're going to need to know how to write problems as we look at different examples today. Or if we're going in the reverse order, if we're looking at a rational exponent expression and we're looking to change that to radical form, okay, we know that we're going to have our little half box. And we have to think about what is our root, what is our base, what is our power. Okay, a is the base, so it will stay the base. C is the root because it's already on the bottom of your fraction, so C should be the type of root that you have for this radical, and B is your power, so either you can put that power inside next to A, or if you want to, again, use parentheses, that's fine. Okay. Just make sure that everything is placed appropriately. So if that's hard to see, I apologize, but notice that in both cases, C is the root, A is the base, B is the power. So that's what we talked about in the previous video. You should be familiar with that. What I'm going to run through today is some different examples in which we have to use our rewriting as well as exponent rules to tackle different problems. And what I thought might be useful for some of you is to look at how I tried to approach these type of simplifying problems. There's a certain order in which I try to do things. Now, of course, all of these steps are not always needed. Some problems you won't have to rewrite at all. Some problems you will. Some problems you have to use certain exponent rules, some problems you don't. But in general, this is the type of order of the steps that I'm looking to apply to each of my problems and asking myself, okay, do I need to do this step next? Does that apply to this problem? If not, skip it. Otherwise, apply that step at that point in time. So rewriting anything from radical form to rational or fraction exponent form is the first thing I'll look to do, because we do want to try to apply exponent rules to most of these problems that we're talking about. So for that to be the case, we have to have an exponent to work with. We don't want that radical, so we switch out of that if we need to. Apply these exponent rules, and I like to do that in this order. Negative exponents, I just like to flip. I just like to get rid of those negatives and become positive exponents. Product rule is typically what might follow the negative exponent rule, so it's just something that I find is a natural flow. Quotient rule comes right after the product rule. Okay, I think to myself, product rule, I'm adding my exponents. Quotient rule, I'm subtracting them. So again, trying to follow a flow. And the last exponent rule that I try to apply is usually the power rule, because typically if you're using the power rule, you have something inside of a parentheses. And if you simplify that part by doing these other rules first, the power rule becomes much easier. It's probably going to lead to less exponents that you have to work with, less negative exponents especially. So that's the last exponent rule I look to use, and if I have to rewrite my problem one more time, I also try to do that. So let's take a look at some examples and follow this order, seeing what we need to apply and what we don't. So for example, I have a problem that says simplify and write in radical form the following expression. Notice, number one, our problem is already in rational exponent form, so I can skip that first step here. We don't start with a radical, we start with a rational exponent, in which case I move on to step 2, and step 2 is indeed useful here, right? We have a negative exponent. So what does our negative exponent rule tell us? Well, it tells us that if we want to change that to a positive exponent, what you're going to need to do is to put a box around that exponent and its base and move it to the opposite location like we've talked about in the previous video. That's going to move from the numerator to the invisible denominator. Remember, anything divided by 1 basically says the same thing, right? 2 is the same as 2 divided by 1. Same thing here. It's useful to make this visible though, because now, okay, we see where this moves, and our exponent becomes positive. Okay. So I'm not quite done here. I do have a positive exponent. However, notice it says end in radical form. So this is where we talked about at the beginning of this video. You do need to be able to rewrite from one form to the other. And in this case, we're ending with our little radical symbol. So I should have this showing up. And thinking about what is my root, what is my power, what is my base. Okay, x is clearly the base. Y is the root, because the root is like a tree root. It goes on the bottom of a fraction, so y needs to be my root. And 7, so two different ways that you can write this. We talked about them. You can either write that 7 inside the radical, right? You could write it right here, if you would like. Or if you want to end your problem where your answer looks more like this and the 7 is outside, it doesn't really matter. Okay, in both cases, 7 is the power. And if you were to distribute that inside, you'd be doing 7 times 1, which is just 7. So either way you want to write your answer there is fine. But notice that we didn't really have any other exponent rules to use, right? We didn't have our product rule, quotient rule, or power rule in this case. It was only the negative exponent rule. It just depends on your type of problem. So let's look at a different one where we have to simplify this expression. Now, in this case, we do need to rewrite our problem from radical form to fraction exponent form, and that works well in this problem, especially because that's all we're going to need to do inside this parentheses. The first thing that I'm going to do is to change the inside of this parentheses from radical form to rational exponent. How do I do that? Well, I look at my root, and remember, the rule is that the root is like a tree root. It goes on the bottom of an exponent fraction, and opposite of the power rule, which we are going to see later in this example, opposite of that, it's sort of like distribution by division. Here's what I mean. We have that 3, we're going to come back to that later. Rewriting, that 4 is going to go in the denominator, or on the bottom of both of our exponents. So we are dividing in this case by 4. Distribution by division, it applies to both exponents inside of your radical, underneath the radical inside that parentheses. Simplifying from here, we know what 12 divided by 4 is. We know what 24 divided by 4 is. Okay, 12 over 4 is 3. 24 over 4 simplifies evenly as well to a 6. So we've applied step 1. We've rewritten our problem. We came up with rational exponents, which ended up simplifying a little bit further, actually. There are no negative exponents. We can skip that step 2. We're not going to be using the product rule. Notice that these are different bases, x times y. It's not x times x. Cannot use the product rule. We're definitely not dividing in this problem, so not using the quotient rule. So the power rule is what we're going to end up doing here, and in this case, as we've done in previous videos, distribute that outside exponent to both of the ones on the inside by, in this case, multiplication. Division for roots, multiplication for powers. So if you do 3 times 3, and 6 times 3, you should get a pretty simplified answer here. X to the 9th, y to the 18th. Did our problem ask us to write something back in radical form? Well, we don't need to, because these are as simple as possible. So that is not necessary. But it's just an example, another example of why I think the flow of the steps that I'm talking about here is the one that I might recommend to you if you're trying to do these problems on your own. A couple more things that we can talk about where we follow these examples using some different rules. If I was asked to simplify the problem here in green, okay, first thing, once again, look to rewrite your problem from radical form to rational or fraction exponent form. Now, there is another way that you could solve this problem. You could do an exponent rule here first, actually. You could do the quotient rule, which we're going to have to use anyway, and that's what happens in math. Typically, you'll find that you can solve problems different ways by doing one step first versus another, although you end up using both steps. But like I said before, I will recommend that you follow the order that I'm doing, just so you have a sort of pattern that maybe in the future you know how to apply to your specific problem. So, rewriting both the numerator and the denominator. Notice that the numerator is in radical form, as is the denominator. We need to rewrite both of those. Okay. So 3 is the root in both cases. Root, like a tree root, going to go on the bottom of a fraction exponent. That's 21 divided by 3, 6 divided by 3, both of which divide evenly, right? 21 over 3 is 7, and 6 over 3 is 2. And now we look to see what else we can do. Negative exponent rule? No, there's no negative exponents. Product rule? No, we're not multiplying two numbers with the same base. We are, however, dividing two numbers that have the same base. X over x. So, opposite of the product rule, we are going to subtract our exponents. Usually for the product rule, we are adding our exponents. Quotient rule, division rule, subtract those exponents, numerator minus denominator. Okay. Should give us x to the 5th. So we're not dividing our exponents here, we are subtracting them, and that would be our final answer for that problem. That takes us to one of our last examples using these steps. Simplify and put into radical form the following. So we don't need to rewrite the problem in this case. Notice that we are already in rational exponent form. Fraction exponent already shows up. There's no radical, no little half box symbol. There's no negatives either, right? No negative exponents, so you can skip that step. The product rule, once again, does not apply. Okay, A, B, 4, these are all different bases. And yes, 4 is a base. We'll come back to that. Quotient rule also doesn't apply. We've actually skipped almost to the end. The power rule is the one that we're going to use here. But be careful, as we've talked about in a previous video, there's actually 3 exponents on the inside of this parentheses. That 4 has an exponent and it's an invisible 1. Sometimes I see students try to multiply 4 times 5 halves, and that's going to give you an answer like 10. That's not correct. Okay? You're always multiplying, using the power rule, to your exponents on the inside of this parentheses. In this case, that's a 1 that you're going to multiply 5 halves to. So we'll see what that means. We'll see what that looks like. But the rule holds true. Even though it's a fraction, it might look a little bit odd to be multiplying by a fraction. It's not that different, okay, from what we've done before. 1 times anything stays the same. So you will have to simplify this. You're welcome to use a calculator, but I will also explain how to do this, or what it means manually. Okay. Otherwise, 6 times 5 is 30, and 3 times 5 is 15. That's where those numerators are coming from. All right, we have this number here, right? 4 to the 5 halves power. Remember that 2 is like a root, and roots are like tree roots. They go on the bottom. So this right here is really the same thing as if I wrote my problem like this. Remember, 2 means invisible square root symbol. Okay, I could put a 2 here. It means the same thing. That's the square root of 4, and I'm taking that to the 5th power. So what is the square root of 4? Hope we all know this. The answer there is 2. And 2 to the 5th power, 2 times itself 5 times, gives us a 32. Once again, this is not a 10, it's a 32. Okay, so be careful earlier, multiply your exponents, not the base times exponent. So 32 there, if you type that in the calculator, I think that looks something like an A, B button. So if you type in 4 and press this little A, B button on whatever calculator you're using, you should be able to type in 5 halves as a specific exponent, which will give you, once you press enter, okay, equals 32. That's how you use the calculator that you're probably looking at online to type that in. Taking a look at our other variables, Okay, we can simplify one of them pretty easily, right? 30 over 2 simplifies evenly as a 15. However, that last one, b to the 15 over 2 power, okay, that's rational exponent form, and our problem asks us to put the final answer in radical form. So the question is, how do I get rid of this? Okay. Now, if you want to simplify as evenly as possible, what you would do is to say, how many times does 2 go into 15? How many times does 2 go into 15? And the answer you should come up with is it goes in 7 times, but there's a remainder at the end, right? 7 times 2 is 14. If I take that away, this tells me my remainder is a 1. How is that helpful? How is that useful? It's helpful because it's going to be able to take us back to radical form. Okay? In other words, this right here is the same as b to the 7th power times b to the 1/2 power. B to the 7th power times b to the 1, okay, that's your remainder, 1/2 power. How does this take us back to radical form? Well, we've talked about in the past how to rewrite problems from rational exponent to radical form, and there's 2 different ways to write a square root. This is one way to write a square root, but the other way that you can write it, and this will actually be your final answer here, okay, a to the 15th, b to the 7th, and the square root of b goes last. The radical always shows up last in the type of expression that you have. So those are a few examples of us applying those steps to our problem. I want to leave with one final problem that's going to require a bit of extended thinking. Okay? Because in this problem, this will be where we end for the lesson. In this problem, we have 2 different expressions, right? We have a radical expression in our numerator. We have a rational exponent expression in our denominator. And I want you to be able to simplify the left-hand side to be able to match it to how the right-hand side looks like. So how would you do that? So without looking at the steps that we talked about earlier, see if you can figure that out on your own. You would still follow the same steps. Try to solve this first. Simplify this left-hand side, how you think you can, come back, and then take a look at the solution, which I will present now. So first thing that we want to do, once again, always change from radical form to rational exponent form. Now in this case, we don't have to touch the denominator. That's already the way that we want it to look. But for the numerator, you're going to need to change that. Okay. 3 is the root. Roots are like true roots. They go on the bottom of a fraction exponent. Okay, why did I do that? Well, now I'm able to apply some exponent rules. So once again, you always want to rewrite this from radical form to rational exponent form if you need to. That way we can apply the exponent rule. Think about what it is. It's the quotient rule, right? We're dividing 2 numbers that have the same base, x over x. We talked about this in the previous example. What does that mean? Well, we want to subtract numerator minus denominator. Yes, those are fractions. Yes, you guys can do that. You guys are smart, okay? Not that difficult. Remember, we're not doing 3 minus 3. We never subtract our denominators. Okay, we can't divide by 0. We don't want 3 minus 3. What we end up getting there is 17 minus 5 is 12. And that divided by 3 is 4. Now, this is not the final answer. Remember, we were looking to solve for y. So this right here has to equal x to the power of y. What do you think y is going to be? Not too difficult at this point. Just match up where y is on the one side versus where it would show up on the other. And in this case, our answer is clearly 4. Y equals that exponent of 4. So hopefully that illustrated how the 6 steps have a certain flow to them and how you can apply those to different types of expressions. In our next video, we're going to start a new topic. So this wraps up everything from radicals and rational exponents, and I will see you when we start talking about complex numbers.